Oh, sorry, 2.1. I'm excited for actually solving, so I'm writing 2.2.
We got to a point where it only showed up for 6 periods and went home.
We should drop
You didn't come to one class.
I'll just
You
start calling you
can't
Josh.
shoot all of them. Like, well, I feel like once I'm here, I think for like 52 minutes, it's not worth it.
All right, so today we're going to talk about solution curves without a solution. And the entire chapter 2 is about first order differential equations. So we can often figure out important information about differential equations without actually solving them. Sometimes we can't solve them, and we need to figure out that information some other way. We'll talk at the end of the chapter about solving them numerically, but sometimes we can get some quantitative information even without doing that. So we're talking about the behavior near specific points. Behavior as our independent variable x approaches infinity. What is the general shape of a solution curve in the plane? All right, and we're relying on the fact that if y is some function of x, then dy dx gives us the slope of y of x at some point. So in general, for direction fields, what we call direction fields, or slope fields, is we assign a slope to points in the plane. And then we draw small segments at that point, at the points. And the segments have the slope that we're assigning to that point. We call those segments, or the book calls those segments, lineal elements. So we plot those elements. For a number of points. To generate a slope field or direction field. So the slope field or direction field tells us what the slope is for our solution curve at a specific point. So the field suggests the shape of solution curves. And we know we get a different solution curve for different values of or constant. So we can plot different solution curves. It's very similar to when we were looking at vector fields, and we said we could get some information about the shape of the vector field by plotting where we have constant magnitude. kind of a similar way of thinking. So looking at these solution curves, it gives us information about the solution to the differential equation. Now I found it very funny, and I told the other calculus teachers about this because when we're talking about slope fields, when I was in school, we never did slope fields because technology wasn't as big a thing. But our book says something very interesting about slope fields. And you'll come back to this for one of your homework problems. So sketching a direction field by hand is straightforward but time consuming. It is probably one of those tasks which an argument can be made for doing it once or twice in a lifetime. I definitely agree with that. But it is overall most efficiently carried out by other means like computer softwares or calculators. And then it talks about some other things. So I agree that sketching them by hand is not difficult, but it's kind of tedious. Question 15A is our one, in this class, our one chance in our lifetime to sketch a slope field by hand.
If we do it as a class, like,
So they give you
as a person, like as people, we each do the different slopes.
like we did at CalCamp. And they give you a nice method in problem 15A, and in that remark, the continuation of that remark that I read, for a kind of a systematic way for generating a slope field instead of just calculating slopes at random points. So what I've done is in our Schoology class, I found some calculators, and one of them is a slope field calculator. So in general, for generating slope fields, you can use that slope field calculator. I found it's easy to use, and it's pretty straightforward. So let's look, oops, that's not what I wanted. Let's look at an example. So let's say dy dx is the sine of x plus y. A little later in the chapter, we will learn how to solve a differential equation like this. But we want to look at a slope field. So I'm going to go to my slope field calculator. And it comes set up with a default equation in there. dy dx is 2x over y. So we want, I'm just going to change this to sine x plus y. And there's our slope field. So let me grab a picture of that. And this has a nice movable point. So you can move this point around in the plane to find the slope at a specific point. So if we wanted the slope here, we could figure it out. We can see as we move along here, the slope changes. So it's kind of nice. So I'm going to grab a picture here and paste it into our problem. So there's a slope field for that differential equation. And if we wanted to plot a solution curve, the solution curve generally follows the slope as we move along the curve. So if I started here and I wanted to sketch a solution curve, our solution curve would look something like this-ish. Because the slope in here is about between the slope of those two lines. So we get something that looked something like this. And it's not necessary to be super precise with your slope field, but that's a general shape of a solution curve. Let's look at another one. Dy dx equals xy. So I'll go to our calculator, change that to x times y. And there's our slope field. Let me grab a picture of that one. Is it going to let me do this? Oh, it did. I'm going to shrink that down a little bit. So there's our slope field. And just looking at this, what the solution curves, what would you guess the solution curves look like? Yeah, they kind of look like parabolas. So if we were to sketch one starting here, our solution curve would look something like that. And down here, our solution curves would look something like that. And we'll talk about it a little more later. Comes up in a different context. But when the places on our slope field where the slope is 0, we call null clines, because the slope is null. It has no incline. So we have a null cline along the x-axis there. The slope is 0 when x equals 0. And do we have any null clines here? Kind of doesn't look like it, does it? Curves where the slope is 0. 0. No, I don't think so. And curves where the slope is constant are called isoclines. Yes.
What about like the y-axis?
The y-axis would be, that would be y-axis, the slope is constant value 1, except at the origin.
Shouldn't it be 0?
Should be 0.
I think those are
Oh,
just,
no.
those are just the hashes for the
Yeah, the slope is 0, yes. The slope there is 0. Yeah, so on the y-axis is an isocline. Sorry, a null cline. The slope is 0 on the y-axis. And curves where the slope is the same constant value we call isoclines. Yes.
What if the slope's undefined? Like what if it was y over x?
Let's look.
That's x over x.
Oh, then do x over x? The slope is 1 everywhere. So along x equals 0, it's undefined.
Okay. There's just no slope.
Right.
That's true. I kind of like that one.
Yeah, that one's kind of interesting.
Yeah, it looks like you're like kind of zooming into
Mm-hmm.
or it's like
It looks like the Star Wars reference, like the
Right.
speed.
When they jump into.
differential equation y over x.
All right, so questions about using technology to generate a slope field and sketching solution curves. Now for solution curves, we don't have to be super precise about where they are, just generally get a shape of the solution curve. So let's say we want to, we'll talk about an initial value problem. So we want to use direction fields, or use a direction field. Sketch an approximate solution. To dy dx equals e to negative 0.01 xy squared, where y of 0 equals negative 4. So let's get a direction field. So we're going to put our equation in there. So E to the negative 0.01, what did I say, x y squared? So there's our slope field. Grab a picture. And our initial condition is that y of 0, when x is 0, we want to be at negative 4. Did I go down far enough? Is the black one there? Oops. So we want to be here. So our solution curve would be roughly something like that. I guess it should go up a little more before it levels out here. Maybe like this. More like that. But we can see as we go further up here, the slope is getting closer and closer to 0. And let me go back here. Here our slope would go, if I continued, our curve would go down, something like that. So it's kind of an exponential curve-ish. But to do a specific solution curve, we just want to make sure our curve goes through that one point that we're given, our initial value. All right, we're good there. This is nothing too complicated here. Sketching the slope fields is actually more difficult than working with them, I think. Not difficult, just more tedious. All right, so one special kind of differential equation that is nice to work with in terms of getting information without a solution is called an autonomous differential equation. So an autonomous first order ordinary differential equation is one that we can write as dy dx equals some function of y. Or, if I write it in our other form, f of y comma y prime equals 0. So this is a function of y only. So this is an autonomous first order ordinary differential equation. So dy dx equals y plus y squared is autonomous. Because this is just a function of y. Dy dx is equal to x cosine y is not autonomous. Because this is a function of x and y. So autonomous means where our derivative is just a function of the one variable. Autonomous differential equations are nice because we can say a number C is a critical point if f of C equals 0. And this is because, or this implies, if f of C equals 0, dy dx equals 0 at that point. So that's why we call it a critical point. The derivative is 0. If f of C is 0, then dy dx equals 0. We also call this point an equilibrium point or a stationary point. And we call it an equilibrium point or a stationary point if we think of some curve. Well, we're at a maximum or a minimum. At that point, our function is neither increasing or decreasing. It's at equilibrium. It's stationary for an instant. And the important thing about a critical point is that if C is a critical point, of dy dx, an autonomous differential equation, equals f of y, then y of x equals C is a solution to the differential equation. So by looking at the critical points of our autonomous differential equation, we can find equilibrium solutions to our differential equation. Yes?
Is that like a singular solution?
Singular solutions can be equilibrium solutions, but singular solutions are not necessarily at equilibrium points. I think the singular solutions that we've seen have all been constant solutions, some kind of constant solution, but it's not necessarily that way. All right, so let's look at an example of dealing with this equilibrium solution, this equilibrium point, etc. So if we have dy dx equals y squared minus y to the third, and we want to find equilibrium solutions. So I'm going to rewrite this. Dy dx equals y squared times 1 minus y. So the equilibrium solutions are y equals 0 and y equals 1. We're looking for where this derivative is 0. When y equals 0 and y equals 1, we have dy dx equals 0. We have an equilibrium solution. So let's look. I'm going to sketch a little, sketch the plane. And here's one equilibrium solution at y equals 0. We know the slope is 0 there because dy dx equals 0. And here is y equals 1. We can get information about how this differential equation behaves in these three areas of the plane. So when y is less than 0, so down here, we can plug in some value less than 0 here. Is our slope positive or negative when y is less than 0? So this is going to be negative. If this is negative 1 minus, so this is a negative times a positive, right? Or is that, did I do that right? This is positive. Positive times a positive. Because if y is negative, y squared is positive, and 1 minus negative y is going to be positive. So that is going to be positive. So anywhere below here, our slopes are positive. So in general, our solution curves are going to do this. They have always positive slope, and they're going to approach 0. The slope is going to approach 0. When y is greater than 1, is the slope going to be positive or negative? Right, this is going to be positive, but this quantity is going to be negative. So in general, our solution curves are going to do this somehow. And then in between, if 0 is less than y less than 1, so if we plug in a number between 0 and 1, this is always going to be positive, but this will be positive. So in here, our slopes are generally going to look like this. So we have, just from that information, we have a rough idea of what our solution curves are going to look like in those different areas of the plane. Yes?
Do you remember that, like you know how on top one when we did like critical points, you had to like look on the other side of critical point to make sure that like the slope changes? Because for a function like x cubed or something, there's actually
That's kind of what we're doing here.
okay.
So this point here at y equals 1, because the slopes for values less than 1 and the slopes for values greater than 1 both approach the slope at y equals 1, we call y equals 1 an attractor. And sometimes you hear it called a stable attractor. All the solution curves are attracted in that area, are attracted to y equals 1. And we call y equals 0 because some go towards y equals 0 and some go away. We call y equals 0 is semi-stable. And if the slopes are both on opposite signs on either side of a point, so the slopes, the solution curves are going to go away. So if the slopes here were negative, so the slopes are always going away from y equals 0, we call that a repeller. I'm going to say opposite signs away, not opposite signs towards. So we have attractors, semi-stable critical points, and we have critical points that are repellers. That's what the last problem says. You don't need to use the phase portrait. The phase portrait is you kind of draw a little picture of what's happening with the slopes on either side. I like just drawing a little picture like this and just thinking about what's happening with your solution curves. Essentially, what we've done here is make a phase portrait, but it's not technically a phase portrait. So we have these attractors, semi-stable points, and repellers when we're talking about critical points. But often when we have an autonomous differential equation like this one, we can factor it in some way to find the zeros, to find our equilibrium solutions. Once we have our equilibrium solutions, we get some general information about the solutions themselves without actually solving. And these points, again, where the slope is 0. So along y equals 1, we have a null line because the slope is 0 along there. And again, the curves along which the slope is constant, we call isoclines. And the isoclines are how we, in problem 15, is how we're going to sketch that slope field in that particular problem. Sketch curves, and you sketch a constant slope along that curve. So you sketch various curves and constant slopes, and you get a decent picture of the solution curves. But I'll show you my solution here. Where is that one? There. You can see that there a lot of erasing went on there. So, all right, questions? Okay. This section 2.1. And 1 through 15A, odd. And for these two, we're looking at the equilibrium solution only. And for number 41, you don't have to use the phase portrait.
Like go through number 9. Like I was just doing homework last night and I was just like struggling.
Which one is
1.3.
Oh, let me stop this. I think that's what that happened.